Log on, tune in, find out. Another good idea from Cambridge.
Okay, so I guess I should start. So just to remind you, in the first lecture we sort of motivated this time reversal function in the context of least squares inversion. And so now the question is, can we use this for imaging? Okay, so the idea would be that if we knew the medium, that means we could compute this Green's function, then we could form an image which will be the sort of time reversal image, which will amount to basically taking the data that we measure, we back propagate it to the points y at which we form an image, okay? And then we observe this function for as we vary the point y in a search domain, and then by looking at the if this is to work, then we would expect that this will focus at the point y, which will be hopefully a good approximation of where the scatterer is, or in the case if we did a source problem, where the source is. Now, as I mentioned in the beginning, we are interested in imaging in inhomogeneous media. So here are two examples of such media. So this is a plot actually of a wave speed profile in the Earth. So this is, people make sort of these wells and then they measure the wave speed, and this is how it looks like. You see it's highly fluctuating. And this is a plot. This is actually numerically simulated, this medium, but this is supposed to be an illustration of how sort of scattering media may look like. So I think a very good application will be if you think in the context of non-destructive evaluation. So think of this as being a chunk of concrete, and then here we plot the wave speed, and with colors we show the fluctuations of the wave speed. So you see you have sort of fluctuations due to inhomogeneities that will be little rocks and so on. Okay? So now the point is, what can you do in this case? Well, certainly you are not going to be able to know all the details of the medium. Okay, so there is no way, I mean, and we don't have data like that. And that is why what we do is we model this medium as random medium. Okay, so we are going to write eventually, so the wave speed v, the background speed, okay? So this wave speed now, we are going to write it in this form. So this C naught here is supposed to represent the smooth part of the medium, which is the stuff that you may know. In this talk, C naught is going to be a constant for the same reason that Andreas mentioned, because otherwise it's complicated to compute this Green's function, and certainly you cannot write it down specifically. So I'm going to take a constant C naught. And this function mu is the function that is going to model the fluctuations. And I'm going to say a little bit more about this random stuff in just a second. Okay, but that's the point. So bottom line, we don't know V, we will only know C naught. So the time reversal function, which is this one, cannot be implemented. Okay, so that cannot be done for imaging. And so that's why, you know, when you hear about time reversal, that has nothing to do with imaging in complex media like this, because you cannot really compute it, right? You don't know what G is. Okay. What Matthias Fink has done, he has done an experiment. So what he has done is he had a source, the source emitted a signal, that signal went through a scattering medium, then he captured it at the array, he sent it back, and he stayed near the source and he observed the field. So that's different. Of course, we cannot observe the field, because if we could go near the source, there would be no point to image, right? So that's the difference. Okay, so what do we do instead? Well, the obvious thing will be to backpropagate the field in the smooth medium, which is the only part that we know, and then we end up with an imaging function which is known as migration, or in fact it's called sort of reverse time migration. Okay. So here the backpropagation is in the smooth medium with a Green's function G naught, which for me is going to be the Green's function in the homogeneous medium, but otherwise it will be in the smooth medium. And an even further simplification of that is the one where you approximate this way. So this is a high frequency approximation, and where that comes from is essentially from this. So if you think about it, so the Green's function G naught is given by an amplitude alpha naught, and then you have e to the I omega tau. Tau is the travel time between the points x and y. Right? So for example, in three-dimensional homogeneous media, it is this alpha naught is 1 over 4 pi x minus y. Okay, and then in two-dimensional media, you have sort of like a square root and so on. So this factor is the geometrical spreading factor. And the point is that typically in these applications that I talk about, you have an array here, and then you want to image far away, and the size of this array, which is what we call aperture, is very small with respect to this distance. And then because of that, you can really approximate this amplitude by a constant, really. Okay, so for all the points in the array and for all the search points that are going to be sort of near where you want to image, you can approximate this by a constant, so you can forget about this amplitude, and then you end up with travel times. And so that's what motivates this further simplification, and this is known as Kirchhoff migration. And so it just amounts, if you see here now, so I replace these Green's functions by just these phases, and so this is now easily seen that in the time domain, what this really amounts to is taking the data that you measure at the array and evaluating it at the expected travel time that it will take to go from the source to the point at which you form an image and then back to the receiver. Okay, so this is the Kirchhoff migration image. Okay, so this is the simplest imaging function. It's widely used in geophysics, in radar, so on. This is how this looks like for the source function, for the source problem. Here you only have travel time from where you think is the source to the receiver. Okay, so now what about what we propose? So we propose a modification of that imaging function. So this is a methodology which we introduced some time ago, and we call it coherent interferometric imaging. And this method looks like this. So you see, it's sort of, so it's different than the Kirchhoff migration method because it essentially is quadratic in the data, right? So it works with, so what you're really doing here is you are computing cross correlations of the data. You are not working with the data itself. So I think a particularly easy to understand expression is the one shown below. So it turns out that, okay, so, let me say here. So here in this expression, okay, so this is the data, so, and this is the imaging function for the source problem, okay, so this is a simpler one. For the scattering problem is going to be on the next slide. So this is for the source problem, okay, so this is the data, and then you take the data, this is the complex conjugate of the data, evaluate it at different receivers and different frequencies. This part here is the backpropagation, which is exactly as in the migration function. But then what you have here, you have these two functions. These are window functions. So you can think of phi and psi as being functions with support of order 1. And then you see here that I introduced two parameters, this omega and this x. So this sort of scale the offset in the frequencies, omega and omega prime, that we consider in here, and this scales the offset between the receivers that we consider in here. Okay? So sort of so if you look at this expression, so if you are in this case where this x here, so if we want to choose this x here, this scale, this length scale x, to be independent of the frequency, then we can take this out of the frequency integrals, and then after you do some trivial algebra, you find this expression. Okay? So this, I think, is kind of interesting, this expression, because what it really tells you is the following. So you see, what you are really doing in this imaging function is you're taking the data, and then you are evaluating the data at the travel time, but not quite at the travel time. And the reason is because when you have this scattering media, you are not going to be quite sure when things will arrive, right? So then what you're doing instead of just evaluating this data precisely at the travel time that you think it is, you allow yourself some freedom, and so you take some sort of shifts in this time, and these shifts are going to be varying over the support of this window. Okay, so that's the idea. Okay, so this is the coherent interferometric method. So, and this is how it looks like for the active arrays, kind of the same idea, just slightly more complicated. So, the goal of this course will be to analyze these two methods, coherent interferometry and Kirchhoff migration, and to show to you with rather explicit calculations why is it a good idea to use coherent interferometry versus migration in this random media. So before I go into all that, let me just show you some simulations so you see that this all works before I. So this is a numerical simulation which considers, so in this case, this is a numerical simulation that Crisula Tsonga has run. She has a very good code to solve the wave equation in the time domain. It's a finite element code, and this is the sketch of the computational setup. So you have this computational domain. Here, this absorbing medium is just because this is what you call just to simulate an infinite medium. Numerically, you can't do that, so you introduce sort of this, what is called a perfectly matched layer to sort of make sure that you don't have bounces from the boundary. And this is the array, and then you have here 3 scatterers. And this is how the data looks like. So this is a typical way of displaying the data. These are called seismograms or traces, time traces. And let me explain to you what I'm plotting here. So what I plot here is the pressure P that you measure at the array. Okay. So here in this picture, I have one illumination from a single source, which is the source here in the center. And then I plot with respect to the receiver locations that are here on the horizontal axis, and with respect to the time that is here on the vertical axis, scaled by pulse widths, I plot the magnitude of this P. Okay, so with a grayscale you see that. And here is what the data looks like if you don't have inhomogeneities in the medium, so if you have a homogeneous medium. So what you see is sort of this hyperbola. Okay, so if you look at this as functions of the receiver's locations, you see these hyperbolic events. So these 2 strong ones are the direct arrivals of the scattered waves from these 2 scatterers in front. Then you have also, but then you also have some other stuff that comes, and those are the bounces, the multiple bounces between the scatterers. That's not captured by the Born approximation, of course. Okay, so so really the Born approximation just catches this first stuff, and then probably the strong stuff in the back, which will be the scattering from the one in the back. Now, here is how the data looks like when you have a scattering medium. So this is a simulation run in the medium that look like the concrete structure. So that's how the data looks like, and you see that it's very different than what you have here. There are sort of distortions of the wavefronts here, and then there is a lot of stuff over here before anything from the scatterers come, and then there is a lot of stuff after that. So that is scattering by the inhomogeneities. Okay? So for example, if you take a time trace, so this is a plot of a time trace as a function of time here, so you see a lot of stuff here. So these things, well, it should be, so this is what is referred typically as coda. So this is the multiple scattering effect. Okay, so now here is how migration works. So this is a Kirchhoff migration function, so that's just taking the data, evaluating at the expected travel times, and summing over the array sources and receivers. So this is how the image looks like in the homogeneous medium. You see that it has peaks, and the peaks are in the right location. So here we denote with these black dots where the scatterers are, and so you see that this simple function does a good job of indicating where the scatterers are. Now, this is how the picture looks like when you do it in homogeneous medium. So you see that the picture is very, very noisy. You have peaks in a lot of places. And what is really disturbing is that if you try to do this in a different inhomogeneous medium that visually looks the same, so in other words, if it has the same statistics, this picture will be radically different. All right, so that's what we call, it doesn't have statistical stability, right? So of course, what we want is we want to come up with a method that is capable of estimating the location of the scatterers, and it works the same way no matter what is the realization of the random medium, and so that will be useful. Okay, so here is a comparison. So again, this is the Kirchhoff migration method that I just described, and this is what coherent interferometry produces. Okay, so you can see, so this is an illustration of the fact that, how this method works, but of course there are many questions. Why is it that it works? How should we choose? So this method is more complicated. It has all these parameters. You see it has these sort of windows. How should we choose these windows? How should we choose these parameters and so on? But if you do it right, this picture is supposed to illustrate to you that, this works. So now, basically, what I want to do is to go through a rather explicit calculation and explain to you why this works. And, there are various ways. So really, the mathematics, a lot of the mathematics goes into the model. So the model, into deriving a model. What does that mean, the model? It means to understand in a quantitative way what is the effect of the random medium on the data that you measure. So that's what you need to do. So now, because you have a random medium, then this is going to be a random function, and what you want to do is you want to understand, everything you can about this random function, and then once you do that, then you are going to be able to design intelligent imaging methods. So that's the idea. Okay, and there are various, so first of all, there is a lot of work done, but let me tell you, the problem remains wide open. So there are very few cases that are really understood. And these cases are like this. So the first one that is really understood is the case of layered media. Okay, so the case of layered media, when you have, these fluctuations are just a function of depth, let's say, in the Earth, then the theory of wave propagation in layered media is really, really well developed. Okay, so this is the best understood. Now the second one, even though it may not seem so, it turns out that a lot of the techniques that are developed for layered media apply to waveguides. Okay, so that's wave propagation in random waveguides. So this is a problem that I'm not going to talk about here, but I did that last year. So, I would be happy to talk to you about that. And, there are lectures available, I guess, from MSRI. So now, in terms of general three-dimensional media, well, not so much is done. So I'm going to basically mention the two regimes here that where something is understood. The first one is a very simple, is actually the simplest model you can come up with, which is known as the random travel time model, which is a model that only captures wavefront distortions. Okay, so essentially what I mean by that is the following. So if you have, let's say, one source, okay, and then you measure what comes at the array, if you think in terms of the traces, right, so you plot them as a function of time and receiver locations, okay, how do these traces look like? Well, you are going to see a hyperbola if you don't have, right, so there is these plots that I showed before. Now, if you have a random medium, well, so what this model says is that because of the scattering, you are going to have wavefront distortions. Okay, so this is what this model captures. It does not capture the stuff that comes before and the stuff that comes after. So you need more sophisticated models for that. Okay. So now, where is this model useful? Does this ever occur in practice? Well, yes. So there is a huge field in imaging which is known as adaptive optics. Okay, so this sort of is something that in astronomy. So when people try to see stars, right? So the star will be a source, and then what happens is that as light propagates through the turbulent atmosphere that is sort of near the Earth, that's a thin layer, and it turns out that the effect of that on the wave field is simply a wavefront distortion to very good approximation. And then there are techniques to measure, actually, there are ways to measure these wavefront distortions and in real time correct for that. That's why it's called adaptive. And then, so if you correct this wavefront distortions, you will be able to construct images, very good images. So that's the idea. So this random wavefront distortions appear in this field. So that's the model that I'm going to spend most of the time, because it will allow me to do very, very explicit calculations. And then in the end, if I have time, I will talk about a more sophisticated model, which is there we have to go to the PDE, and this is called the paraxial model, where this is a model that can capture sort of this coda, but it's still a model that applies to sort of mild scattering, that is because the waves will be only scattered in a sort of forward direction. So this paraxial model is essentially the state of the art right now in wave propagation in random media in terms of rigorous mathematics, and everything else is wide open. So it's a good area. Okay, so let me start talking about that. So now, in order to analyze these imaging functions, I need to sort of set up the geometry. Okay, so I have so I'm going to make some simplifications here. So I introduce a system of coordinates. So I'm in n+1 dimensions. Okay, so I'm going to use this notation. So x with an arrow is going to be a vector in n+1. And I distinguish, so I'm going to write it in the form x and xn+1. And this x is an n-dimensional vector, and this xn+1 is what we call the range direction. So this is the direction of propagation of the waves. Okay. So now the array, this is the array, and so what this is a set in Rn+1, and for simplicity, I'm going to suppose that the array is orthogonal to the range direction. What does that mean? It means that the source or the scatter that I want to find is going to be on this axis, and the origin of the system of coordinates is at the center of the array. Okay, so I'm going to make this very simple. So this will be y star, and so according to our notation, this is going to have no offset in this direction. So the direction of propagation is called range, and everything that is orthogonal to that is called cross range. Okay? And so the cross range of the location of the source is 0, and the distance from the source to the array is called L. Okay, so that's the distance. Now, the points in the array so by my choice, they are going to have 0 range coordinate. Okay, because the range axis originates at the array, and this is orthogonal to it. So XR are the points in the aperture. Okay, now we are going to, so because of this simplification, even though, so I call the data little p t of xr, but really now you see this xr I only have cross range here, right? So I'm going to simplify notation. So I'm going to call this capital P of T and XR. So now this is an n-dimensional vector, is the cross range vector. And the same for the scattering data. So that's what is written there in blue. Okay. And so now for the array, we are going to make a convenient approximation, which is the continuum approximation. So we have sensors that are at discrete locations, of course, here. But we are going to, and the separation between the sensors is what I call here delta x. Okay? And what I am going to suppose is that delta x is small enough such that when I form this imaging function, so you saw that all the imaging functions involve sums over the receivers, or if I have the scattering problems, receivers and sources. So instead of working with the sums, I'm going to make this approximation. So this will be like Riemann sums. So I'm going to make this continuum approximation. Okay, so I'm going to work really with integrals over the aperture. And then I will drop, for simplicity, the scaling constant. Okay, so wherever I had sums, I'm going to simply write integral over the aperture. So that's the continuum approximation. And then the linear size of the array, so you can think of the array, for example, in 3 dimensions, then this is just like a sort of a square, and the linear size of the array is a scale that is important, and that is called the aperture. Okay? So that's the setup, and then we are going to compute this imaging function at points y, which will be points that will take value in a search domain that will be around the location of the source that we want to find. And we call these points, so here is going to be such a point y, and then we write the points y in terms of offsets from the true location. So the offset in cross range is c, and the offset in range is eta. Okay, so that's the convention. Okay, now I need to tell you a little bit about the model. So first of all, I don't really know what to assume about how many people are familiar with probability theory. Okay, so it's less than a half. So please bear with me. I will try to give a very brief crash course in that. I'm just going to sort of introduce concepts that I'm going to need. So, okay, so here it goes. So whenever this is what we call a probability space. Okay, so what do we mean by that? So we are trying, so imagine an experiment. So I will try to use as an illustration the following experiment. Suppose that you have 2 dice and you roll the dice, right? And then you're trying to model what is the outcome. So now this omega is what is called as the fundamental set, or the sample set. So what does it mean? So it's the set of all possible realizations. Okay, so in the dice experiment, it's that, right? So each dice can be anything can give you an outcome from 1 to 6. Okay, now, so we have realization. So typically, so I apologize for this. I'm trying to stay consistent with the typical notation in probability. This is, of course, not frequency now. Okay, so just for this. So this omega is what we call a realization. So in this example, what would be a realization? Well, if you roll 2 dice, and an example of a realization is 1, 2. Okay, so one dice goes to 1, and the other one goes to 2. So that's an example of a realization. Now we also talk about events. So what is an event? So here is an example. We're talking about an event. Let's say, the event that the sum of the dice is bigger or equal than 11, let's say, right? So what will be this event? Well, it will be the set consisting of the realizations 5, 6, 6, 5, 6, 6. Okay, so that's an example of an event. Okay, so that's that. Now, sigma is what is known as a sigma algebra on the sample space. So what does that mean? It's just a collection of sets of events that has the following property. So sigma is not empty. It's closed under complements. What does that mean? It means that if I have one event in sigma, then the complement of that event is also in sigma. And it's also closed under countable unions. So that means that if I have A1, A2, blah, 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 all these events in sigma, then the union of these is going to be in sigma. Okay. Now P is the probability. So this is like a measure. So it's the probability that acts on the sigma algebra and takes values in 0, 1. And what you need is that, so if you look at the probability of the whole space, that has to be 1. And then if you have disjoint events, okay, then you have that the probability of the union of these events is the sum of the probabilities. Okay? And so, for example, in the experiment with the dice, what will be the probability of whatever events of, for example, what is the probability that when you roll the dice, ij comes about? So that's sort of like the uniform probability, and so that's 1 over 36. That's an example. Okay, so now we are talking about random variables. So what is a random variable? A random variable is simply a function on the sample space with values in R. So if you take any realization, x of omega is just some real number. Okay? And for this, we are going to talk about the distribution of this random variable, the cumulative distribution, which is defined as the probability that x is less or equal than the value x. And really, in this course, we are going to talk about continuous random variables, which means that this distribution has a density. Okay, so I'm going to call little f is the probability density function. And so what that means is that if I look at f of x, then this is integral from minus infinity to little x of f. And we are going to talk about expectations of functions of x. And those will be given by this. Okay? So that's for random variables. Now, of course, so here the fluctuations, I model them with this mu. Now that's what we call a random process. So what is a process? Well, a process is nothing else but a parameterized, sort of parameterized random variables. You can think of them like that. So really, what I should have written there is, so if you talk about a random process, so mu is really a function of x and omega, the realization. Okay, so omega takes values in the sample space. And what this really is, so for any given realization, what is mu is just a function from Rn plus 1 to R. Okay? So that's the process. And so we are going to, so you can characterize the distribution of such a process is characterized by moments of the form okay, and this should be for any m. So in order to sort of, so if you know such moments for any m and for any points x1, well, I should put vectors, m in Rn plus 1, and for any functions phi that are continuous and bounded, then you know the distribution. Okay, so we are talking here, so that's what I said there. So I say we are modeling the fluctuations with a random process, so now we know what is a random process that is statistically homogeneous or stationary. What that means is that if you know the statistics of mu of x, and now if you look at mu of x plus x naught, so if you consider translations of this process, okay, the statistics is the same. Okay, so there is invariance under translation. So that's what stationary means. And also now it will turn out that a lot of the mathematics that we do here will have to do with, so you will see that we will take certain limits, and those limits are going to lead us to Gaussian processes. Okay, so what is a Gaussian process? So a Gaussian process is just it's a process that is determined by its first two moments. So if you know the first two moments of the process, then you know everything about it. So all you need to know is the mean and the correlation. Okay? So this is a Gaussian process. Turns out that if you take Gaussian processes, you add them up, you still end up with Gaussian processes. And a particular interest is of a particularly important Gaussian process that we will encounter here is the Brownian motion. So I'm going to denote Brownian motion by B. So what is a Brownian motion? Well, Brownian motion is a Gaussian process with mean 0. So this is Gaussian process sort of, normalized Brownian motion starts from 0. So it has mean 0, and it has correlation so this notation means the smallest between z and z prime. Okay, this is the smallest between z and z prime. So that's Brownian motion, and that is, of course, it's widely studied. So one thing to keep in mind about Brownian motion, so this is a process, of course, I neglected to write omega anymore. We usually drop that notation. But what it really means, so what you should know about this, so any realization of this process is continuous. It's a continuous process, but it's nowhere differentiable. Okay, so this is, and that actually becomes quite important. And if you look at increments of this process, so if you consider a sequence of points, Zn bigger than Zn minus 1, bigger than Zn minus 2, and so on, and then you look at increments, which are Bzn minus Bzn minus 1, and then Bzn minus 1 minus Bzn minus 2, and so on. If you look at these increments, they are Gaussian, and they are independent. They have mean 0, and also, if you look at sort of the variance of these increments, so Bzi minus Bzj squared, then this is just, well, maybe I should put Zj, j minus 1, so then they are ordered already, so this is Zj minus Zj minus 1. So we will encounter this process. Okay, so so that's how I'm modeling my fluctuations now. So I'm writing the wave speed as consisting of a smooth part. C0 is taken constant for simplicity. And this models the fluctuations. So now mu is a process which has mean 0. Now we know what that means. Is statistically homogeneous or stationary. We also know what that means. It has an autocorrelation which is defined this way. So because of stationarity, this moment only depends on the difference between x and x prime. Okay, so this is the autocorrelation. And we are going to normalize this autocorrelation. So we suppose that this mu is a normalized process where the normalization is done this way. So what does this mean? It means the following. So of course, so if you look at the mean of the fluctuations, that's clearly 0, right? That's what I say. Now, if you look at the intensity of the fluctuations, as I model them there, well, sigma is just a number, so it gets out. And now you have the expectation of mu squared, and that is just the autocorrelation evaluated at 0. And so I set this to 1, and this way, then you can see that sigma squared is in fact the intensity of the fluctuations. Okay, so that's the intensity of the fluctuations. So sigma models how high are the fluctuations. And then if I look at the autocorrelation of these, so sigma, forget it, we already know what that is. So now if you look at this, then this is the autocorrelation with arguments scaled by L. And what we assume here, so that is really an important assumption, is that what we say is that this median that I use here lacks long range correlation. What that means is that the correlation function R is integrable. Okay, so you may think of this roughly, okay, so of course it's not quite right, but you can think of this R as having compact support of order 1. Okay, now when I introduce this model this way, you see that if this has support of order 1, because I introduce this scale, the support of this one is going to be order L. Okay, so this is the length scale that tells me what is the correlation of the random what is the correlation of the values that this random function takes. And this L is called the correlation length. So it roughly measures what is the size of the inhomogeneities. Okay? And so all this, so this is really all I need. And then for the purpose of this course, because I want to do explicit calculations, I am going to take a very particular form of the autocorrelation function, which is this Gaussian. This does not mean, of course, that mu is a Gaussian process. It just so it doesn't mean that at all. It's just the form of the autocorrelation. Okay. So, well, I think I have to stop. And so next time, I will introduce the random travel time model and analyze the imaging functions.
Any questions immediately? Perhaps you go lunch or something.